All right, hello everybody. This is Cezar Lupu, a professor at Texas Tech University, and he's going to be giving us a seminar on Robin's inequality and superabundant numbers and the Riemann hypothesis and how they are all connected.
All right, thank you very much for the introduction. Well, I'm just gonna start diving directly into the subject. Well, I would like to talk about one of the most important problems in mathematics. Probably you have heard of this. This is a very famous problem, which is called the Riemann hypothesis, but I'm not going to talk too much about it. I'm just going to talk more about an elementary version of the Riemann hypothesis, something that it's more appealing to an undergraduate student. And well, there are a couple of them, and I will talk about them. So let me just say, so we're going to talk about Robin's inequality. And this will be one of the equivalent inequality, one of the inequalities which is equivalent to the Riemann hypothesis, superabundant numbers. And last but not least, but I'm going to start with this, the Riemann hypothesis. So what is Riemann hypothesis? Well, like I said, it concerns the zeros, and in fact the non-trivial zeros of a certain function which is defined by a series. So the Riemann hypothesis, I mean, I'm going to abbreviate this from now on. Hypothesis, and I will, like I said, I will refer to this as RH. So the Riemann hypothesis, right? Concerns, so this was stated by Riemann, so stated by Bernhard Riemann, and this was in his groundbreaking paper in 1859. So it was, probably you've heard of this guy, Bernhard Riemann is a very famous German mathematician. Probably you have heard in Calculus 1 about Riemann sums. So the Riemann hypothesis, which was stated by Bernhard Riemann, concerns the complex zeros. And when I would say zeros, complex, and let me be specific here, complex non-trivial zeros. Of the Riemann Zeta function. So the Riemann Zeta function is defined in the following way. So it's a zeta of S, and it will be defined as this series, the sum from n equals 1 to infinity of 1 over n to the s. And this s is a complex number whose real part is greater than 1. Well, that would be surprising to you, but this function will have some zeros. Anyway, I'm not going to delve too much into details about the Riemann Zeta function. You know, it will involve some stuff about complex analysis, and I don't want to do that. That's not the purpose of today's talk. But maybe I should mention a few words about this function. So this is the Riemann Zeta function, as you can see here. Well, initially this was defined by Euler for a real argument, right? Instead of a real part of s greater than 1, it's just add a real number x greater than 1, and you know this is a convergent series and so on. But now this function, the Riemann Zeta function, has this amazing property, this amazing property is called analytic continuation. What does this mean? Basically, analytic continuation, it will allow you to go beyond the domain of definition. So this function, so the Riemann zeta function, let's mention this briefly. Can be extended by analytic continuation, can be extended by this procedure that we call analytic continuation. Right? And to the whole complex plane, to the whole complex plane. And we probably, not too much is making sense by what I'm saying now, well, but once you will take a complex analysis course, I'm sure everything will make sense. So it will be, it can be extended to the whole complex plane where it has only one singularity. So it accepts one singularity. And that singularity is well, that singularity we call a pole at s equals 1. So this is where we have problems at s equals 1. Where for s equals 1, as you can see, this is nothing else than just the harmonic series, which diverges. Well, before I even say about the Riemann hypothesis, in fact, let me say the Riemann hypothesis will concern, so the Riemann hypothesis says the following. In fact, let me write it like this. So the Riemann hypothesis concerns the following. So it says that, states that the non-real zeros, well, we say this non-trivial zeros, but anyway, non-real zeros of the Riemann zeta function zeta of s, right? Okay, I'm gonna write it like this, all lie on this line, on the line real part of s equals 1/2. So all non-trivial zeros of the Riemann hypothesis have the real part equal to 1/2. So that's the Riemann hypothesis. Well, it sounds pretty well, but pretentious at first, but it's very basic. And unfortunately, this is still unproven even today. We don't know how to prove this. If you prove this, you're not just going to get $1 million. It's you're also going to get the Fields Medal easily, and it has tremendous consequences in number theory and and functional analysis, algebra, whatever, anywhere. All right. And like I said, I mentioned at first the connection between the Riemann zeta function. So this is, as you can see, it's stated here. It concerns the zeros of a function, of a complex function, right? But this will have, like I said, equivalences in number theory. And I would like to mention, so from now on, let me abbreviate RH. This will stand for the Riemann hypothesis. Okay, I would like you to look at it. This is what it says. Well, the connection of the Riemann zeta function with prime numbers was first questioned by, so let's mention some historical facts. The connection of the Riemann zeta function right? With prime numbers, because this is what we're interested to see what kind of consequence it has here, was first questioned by Gauss, and what he did by Carl Friedrich Gauss. Probably you have heard of this guy. He's a very famous mathematician. Again, one of the math gods. I don't think that he needs any introduction. He proved he is the biggest mathematics itself, I would say. Him, Euler, Riemann, and some few others, contemporary mathematicians. But these are the gods in mathematics. Well, and the connection that Gauss made was first by the prime counting function. So we'll define, so the prime counting function is defined by this: pi of x is the sum over all, so basically over all primes less than x, right? It counts how many primes, so given a number x, it counts how many primes p are less or equal than x. And the prime counting function, right? Gauss said that pi of x, so Gauss observed that. So let me write here, the prime counting function is defined by this. Also, I'd like to mention that Gauss observed that this function pi, that pi of x, the prime counting function, so this is what we're going to call the prime counting function from now on, that the prime counting function is, well, let's say, well approximated by by the logarithmic integral. So we've heard of the logarithm, but now you're going to see about the logarithmic integral. Of x, well, sometimes it's defined from 0 to x, but I'm going to define it in this way, from 2 to x of dt over log t. And by the way, here log t is nothing else than just the natural log of t. That's what I mean by that, right? So this is what observed. And by the way, this log t, usually this guy satisfies this estimate. It's something like x over log x plus O of something like x over log x squared. So it's bounded by a constant times this guy, x over log x squared, right? So this is what Gauss observed. But later on, the prime number theorem, there is this, the prime number theorem, states that, so I'm going to abbreviate this by PNT, states that this pi of x is asymptotically equivalent, I'm going to write it in this way, with x over log x as x approaches infinity, right? Okay. Well, what do I mean by that? It's equivalently, this means that the limit as x approaches infinity of pi of x over x over log x is 1. That's the celebrated prime number theorem. I think it was conjectured by Gauss first, then Riemann tried to prove it, and then the first proof came in 1896 independently by these two. So the first proof came in 1896, independently by these two mathematicians, independently by, de la Vallée-Pouzin and Jacques Hadamard, French mathematicians, both of them. So, but they use complex analysis, and the first proof that was elementary. So this is so the use of complex analysis. So both of these proofs. Each proof uses complex analysis, but the first elementary proof of prime number theorem came independently in 1934 or 32, something like this, by Atle Selberg, and he was awarded a Fields Medal for this, and Paul Erdős. Right, so these two mathematicians, both of them activated, well, Erdős was Hungarian, Selberg was Swedish, but both of them were in the States. Anyway, so this is the story with the prime number theorem, but Riemann hypothesis gives you actually an error of the prime number theorem, where Riemann hypothesis gives you let's say a refined version of the prime number theorem. So the Riemann hypothesis, let me point out this remark, is equivalent to the following refined version let's say refined version of the prime number theorem. And basically it says says the following. It says that, well, I'm going to write it let's say that for each epsilon positive, right, there is a positive constant that depends on epsilon, and let's just say that this positive constant is C epsilon, right, such that we have the following inequality, and let me write it in this way. So it's such that pi of x minus this logarithmic integral, right, is less than this constant that depends on epsilon times x to the power 1/2 plus epsilon. That's what it says. So this is the one of the equivalences of the Riemann hypothesis. All right. Now, well, like I said, this is a little bit more involved, but there are some other equivalences of the Riemann hypothesis, more elementary. And let me talk about this. So other equivalent statements of the Riemann hypothesis. And I'm going to write it like this. And the first one that I would like to mention, I will mention this chronologically, is it was given by Guy Robin in 1984. So basically says that RH is equivalent, when I say equivalent, if and only if, with the following inequality. Sigma of n is less than e to the power gamma times n log n for all n greater or equal than 5041. So, sorry about that. And here, sigma of n is nothing else than just the sum divisor function. So it's the sum over all divisors of n d, right? And gamma here is this guy, And you'll see that we'll define it in a bit. So this is how it is defined, is this integral. So this is what we call the Euler-Mascheroni constant. Right? And we will see that this constant Euler-Mascheroni is also defined by a sequence which will involve a harmonic number, well, the end harmonic number of the harmonic sequence. And I like, and this is, so this is, let me mention, this is due to Guy Robin in 1984. That's a very nice paper, very underrated and very nice paper. And now the second one, which is a little bit more recent, and it's just, I would say, a slight modification of the first one, of Robin's theorem, says the following, that the Riemann hypothesis is equivalent with the following inequality sigma of n. So the sum divisor function is the same function that is that you see above, is less or equal than hn plus e to the hn, and I'm going to write it in this way, the exponential of hn times log of hn. And this time this will hold true for all, okay, let me write in words, for all n greater or equal than 1. So let me just, so this is Robin, and this is well, this is due to Lagarias, but let me say just here that this guy, Hn, is the harmonic sequence. 1 plus 1/2 plus 1/3, and we'll discuss a bit about this harmonic sequence. Plus 1 over n for n greater or equal to 1 is the harmonic sequence. All right, so, and this is due to Jeffrey Lagarias. That's a very nice, it's a very nice paper and published in the American Mathematical Monthly in 2002. And like I said, it's just a slight modification of the of Robin's theorem. I would like you to look at these two. These are very nice, right? And now I would like to delve a bit about the Riemann hypothesis, right? So you can think of the Riemann hypothesis as, I don't know, if it's true, then you prove that all those zeros, all those non-trivial zeros lie on this critical strip with the real part of S equal to 1/2, or you can say that, well, you can disprove it. You say that there exists one zero that doesn't lie on that critical strip. So instead of looking at this, the initial problem, maybe you should look at one of the equivalences. So as you can see, if you prove one of these two inequalities, then you're done. And you prove the Riemann hypothesis. Okay, and now let me just say a few things about, because I would like to deal with the first inequality. Well, if you, in fact, I proved the second one. I gave a talk a little bit over a month ago at the undergraduate math seminar at the University of Pittsburgh, where I actually proved that the second equivalence due to Lagarias. I presented the paper. And well, I didn't talk about the superabundant numbers and to see how there is a chance for them to disprove the Riemann hypothesis. And that's the purpose of today's talk. Okay, now let me give you an example. For example, for the sum divisor function, right? Let's take for n equals 6. Sigma of 6, let's see. What are the divisors of 6? There are 1, 2, 3, 1, 2, 3, and 6. And we will add them up, and this will give us 12, right? And by the way, I would like to mention that this function, the sum divisor function, it's not like it's increasing. It's like it will oscillate. It behaves, well, it's kind of natural to think of this function in this way. All right, and now, I'd like to say a few things about the harmonic sequence. The harmonic sequence, Hn, is 1 plus 1/2 plus 1 over n, right? And we know that this diverges as n approaches infinity. In other words, the limit as n approaches infinity of Hn is positive infinity. So that's what, well, it's increasing, but it diverges. So that's what you need to know about this. And also, there's one thing that you will need to know about this is that this is well approximated, let's say. So we can say that Hn is asymptotically equivalent with log n as n approaches infinity, right? Okay, now let me dive directly into the subject. So I'm gonna dwell more with the first problem, and I would like to use this and to talk a bit about superabundant numbers. Right? So the superabundant numbers. So let's call the definition. Probably you haven't heard of these numbers, but anyway, it has a definition which will involve the sum divisor function. And the definition is the following, right? A positive integer n is said to be superabundant okay, if we have the following inequality, and I'm going to write it, in fact, let me write it in this way, if sigma of m over m is less than sigma of n over n for all m less than n. So that's what we call a superabundant. Well, you can say that this sequence is increasing. And let me, the first 20, let me list the first 20 superabundant numbers. 20 superabundant numbers are the following. Well, you can say it's 1, 2, let's see, 4, 6, 12, 24, what else? 36, 48, 60, 120, 180, and you keep going. 240, 360, 720, and what else? Anyway, 840, 1260, and you keep going. And what else is there? Like 520, 5040. This is important. And the last one is this guy here. I would like to look at it because this will be important. So these are the first 20 superabundant numbers. As you can see here, surprisingly, I have this 5040. And if you would like to go back to, look what happens here. I have this inequality which holds true if and only if it's n is greater or equal than 5041. All right. Well, there are a bunch of lists of superabundant numbers, and you can check them out online. But these are the first 20 superabundant numbers. And now, I would like to mention the following theorem, and in fact, maybe we can prove it. Theorem, which is, well, it comes from another paper which was proved by Akbari and Frigstad. And this was back, and so these two guys back in 2009, which says the following. If there is any counterexample to Robin's inequality, right? And well, the Robin's inequality, what I just mentioned, and let's say 1, so that you know exactly what I'm referring to. So if there is a counterexample to Robin's inequality, then, and this is important, then the least such counterexample right, is a superabundant number. All right, I want you to look at it, and we will prove this, and you'll see that this will have a consequence in proving, well, in providing some, we'll give you some information about the Riemann hypothesis. Well, let's do the proof. The proof is quite short. It's not hard. So, well, I would like to start with a fact. So it is known that there is no counterexample n to Robin's inequality So when I say Robin's inequality, I mean 1, right? With n between, let's say, and I'm going to take, like I said, I was looking at these two numbers. Keep in mind, these two numbers here. So that's why I wanted to write the first to 20. So there is no counterexample n to Robin's inequality 1 with n between 5,040 and 100,880, right? All right, so we know this. This is a important piece of information. And we know that, so keep in mind that that this guy is superabundant. So let's not forget that. Okay. Now, what we're going to do is the following. Now, we assume that n greater than that number is the minimal counterexample to to the inequality, right? And also assume that, n is not superabundant. That also assume that n is not superabundant. Okay, then, well, I assume that n is not superabundant. Keep in mind that the definition is this for all, so sigma of m over m is less than sigma of n over n for all m less than n. Well, then guess what? Then there is, let's say, a number k less than n such that we have this inequality such that sigma of k over k is greater or equal than sigma of n over n. Okay. And now without loss of generality, we can assume that without loss of generality, we can assume that that k is at least that number 180, right? So it's at least that, it's greater or equal than that. Okay, well, next, note that, well, we can assume this, right? Well, next, we notice that since we have, we assumed that n is not superabundant, so since sigma of k over k is greater or equal than sigma of n over n, right? So using our assumption, and now I'm going to use here Robin's inequality. So this will be, well, since I have this e to the gamma n log n, right? So here it's log n without any n. So e to the gamma log n, right? And this is greater than e to the gamma log k. Okay. Since we have this, right? It follows that k is a counterexample. So k, which is greater than or equal than 180, which is greater strictly than 5040, right, is a counterexample to Robin's inequality. To Robin's inequality. Okay, great. However, we assume that n is it's a minimal such counterexample. So, however, okay, but we assume that n is a a minimal such counterexample. So this is a contradiction. So where did the contradiction come from? Well, when we assume that the number is not superabundant, right? So if such a number n exists, then the least counterexample must be superabundant. So therefore, if such how should I say, such a least counterexample exists, then n must be superabundant. Okay. All right, so that's the proof of it. And well, and I would like to mention one thing from here. We would like to mention the following consequence. Well, as a consequence, this means that we'll have the following inequality. We have that sigma of n over e to the gamma n log n, right? So this means that it's strictly less than 1 plus, and we would like to use an unconditional version of the Robon's inequality, which is given by this guy. So it's e to the 0.6483 over e to the gamma log, and I will denote this by n. And if I replace this n by the largest, the super abundant number, right? Then this will give me, so this will be, well, at some point will be less than, or 3617. So this is what we're getting. So in other words, and keep in mind that to get rid of the Riemann hypothesis, we need to lower this guy here to 1. So we can write this as sigma of n less than 1.013617 e to the gamma n log n. Right? Okay. Well, since I have this inequality and corroborated with some other lemma, well, that I'll just briefly mention now. Also, Lagarias proved the following lemma. In 2002, and he proved that that if Hn is the harmonic sequence, then the exponential of Hn times log of Hn is greater or equal than e to the gamma n log n for all n greater or equal than 3. So now if you put this everything together, or if you combine this with the above inequality, then we can get the following inequality. So as a consequence, anyway, because I don't have too much time left. How much time do I have left, Jared? It's okay if I finish in a couple of minutes? Okay, so as a consequence, well, you can say that the sigma of n is less or equal than Hn plus, so we say this is a refined Lagarias inequality. Is less than 1.013617, the exponential of Hn times natural log of Hn for all n greater or equal than 1. So that's what we can get. Right, I was interested in this last inequality. Because you know Robon's inequality, I said this is true for all n greater or equal than 1. So the way we prove this is the following. So we can use the above estimate and Robin's inequality, but that will hold true for n greater than, I forgot to mention, maybe I should. This is for all n greater or equal than 5041. So you can check by a computer all the numbers n from 1 to 5040. So you can check that this inequality is valid. And then from 5041 for n greater or equal than 5041, you can prove it by hand. So as you can see here, if you look at this guy here, if you lower, you see how close is this to 1? If you lower this to 1, then you're the guy. So you basically solve the Riemann hypothesis. Well, I would have, if I had a little bit more time, so I would have mentioned of how would we prove this lemma of Lagarias. Well, the proof is not, it's actually quite easy. In fact, maybe I should just mention, where does this lemma of Lagarias come from? And it comes from the following sequence. So you know that we'll define the following sequence. So this guy here comes from the following sequence. Gamma of n for n greater or equal than 1 is defined by hn minus log n, right? Where hn is the harmonic sequence, right? And now you can prove this will be, it's a very nice exercise. I usually put it in the homework for in advanced calc 1 or 2 even, to show that this problem, this sequence is convergent. So gamma of n converges to this constant gamma, which is approximately 0.577 and so on. This is what we call the Euler-Mascheroni constant. Anyway, I don't want to get into the proof of this. It's just an application of the monotone convergence theorem. So I'll leave it to you as an exercise to show that it converges to this. And with that being said, I will stop here. Thank you very much. If you have any questions, let me know.
Thank you very much.
All right, guys. Okay.